Okay, class, now we're in my muscle 3. In my private website, my muscle 3. Okay, let's see what we have here now. Let's just walk through. Force of contraction. The force of contraction is affected by the number of muscle fibers stimulated. Recruitment. Remember motor units. Obviously, let's take your biceps. The more that you recruit in your biceps, let's say, the more contraction. Remember we had that little hypothetical, I said the 50-pound thing, that each fiber would do this and so forth. So a large number of muscle fibers activated. That's going to give a stronger contraction rather than having a few. Then, what's the size of the fibers? All right, let's talk about this here. Now, after a certain age, when you're very young, skeletal muscle cells do not multiply. Remember, they are multinucleated. So the cells kind of joined together and made it longer. That's why it was multinucleated. So if you start lifting weights, and we've said this before, how does your arm get bigger if you're lifting weights? Each muscle cell starts getting bigger. You're not mitosin adding muscle cells. Each one gets bigger. Remember, that's what we call hypertrophy. Hypertrophy is increasing the size of a cell. Remember, we talked about hyperplasia, increasing the number of cells, and hypertrophy. Now, if your arm gets bigger and you get stronger, then what does that mean? That the reason the muscle cell got bigger is because you started doing protein synthesis and putting more actin and myosin in there. If you do that, you put more contractile components, and that's what's making you get stronger. Okay? If your muscle hypertrophies and you don't get stronger, then what's making it larger? You just add an extra glycogen to give you a little more endurance. So in other words, to get stronger though, you'd have to increase the muscle size, cell size, hypertrophy, but by increasing actin and myosin. Okay. All right, we'll go a little further then. The force of contraction is affected by the frequency of stimulation. We're back to temporal summation. Remember temporal summation? Okay. Frequency of stimulation. Length-tension relationship. Let's go to that. Remember this one in the last one. I said, why is it, so let's go to this picture. Why is it if you're like this, you don't have as good a contraction force or like this? And we said that that's because in these sarcomeres, see, to get contraction, a good contraction, every myosin head needs to touch to actin. But if it's scrunched in this far, let's use this one. If it's scrunched in that far, look, you can't get to that actin, these myosin heads. The sarcomere is too short. If it's like this, you certainly can't, because most of the heads can't touch the actin. So right in here is what we call the optimal sarcomere length. This is what we call the length tension curve. Here's the length, here's the tension. Length tension. Muscle contraction when muscle fibers are 80 to 120%. Okay? 80 to 120%. Right there. That's what we call optimal sarcomere length. Optimal sarcomere length. Okay? So we go further now. See where we are now. Influenced by muscle type fiber. Load. That's what the muscle is having to work against. So now we're looking at the velocity. How fast can you lift a weight, let's say? And how long can you lift it? Let's make it in everyday talk. So the factors that say how fast and how long are influenced by the muscle fiber type we're going to talk about in just a second. How heavy is the weight? Now, you don't even have to take this course to know that. If you're dealing with a real heavy weight, it takes longer to try to lift that thing. And then finally you keep exerting, and you lift it. Now, of course, going back, if you keep exerting, and you don't lift it, then you're doing an isometric what? Contraction, which we've talked about. And then recruitment, bringing in extra motor units. So let's see where we are. All right. Muscle fiber type, classified again by two characteristics. Speed of contraction, slow or fast, according to speed at which myosin ATPases split ATP. Let's go over here. All right, here's ATP catabolism, breaking it down. ATP breaks down to ADP plus P plus about 7,300 calories per mole. Remember, mole 6.02 times 10 to the 23rd. You need the enzyme to break it down effectively. Now, it'll break down on its own, but then everything will go away as heat. Remember we talked about efficiency just a moment ago? How much work do you get out of the ATP? All right. Now, there are different ATPase enzymes. We talked about isoenzymes. Same enzyme, but doing it a little differently. Some work fast and some work slow. Some work fast, some work slow. The fast ones break down ATP fast and release energy fast. Now, when energy is released fast, most of that energy, a lot of it goes away as heat. So we don't have as much efficiency like we talked about. When the energy is released slowly, though, you harness more to do the work, so a better efficiency. So if you break it down fast, that's for fast muscle. But for muscle that needs the endurance, like your biceps is fast, but your postural muscles, you want endurance. So you want to get as much out of it as you possibly can. Pattern of electrical of the motor neurons. Okay. Now, let's talk on that. Okay, motor neurons. Let's see what that is. You haven't done nerve yet. You've done some when you should have been looking at electrophias, but some neurons are motor and some are sensory. Motor neurons turn on, called innervate something. Somatic motor neurons innervate skeletal muscle, turn it on. Autonomic motor neurons innervate smooth muscle, cardiac muscle, and glands, to be looked at later. Some motor neurons are faster than others, depending on the diameter of the fiber. The diameter of the fiber. The bigger the diameter of the fiber, the faster the motor neuron. The larger the diameter of the fiber, the faster the motor neuron. And if it's myelinated, we haven't talked about that. Myelin is a coating around neurons. We'll introduce that in our nervous system tissue chapter. Okay? So in other words, but the point pattern of the motor neurons, because since the skeletal muscle has to be turned on by a neuron, then the faster the neuron, the faster you can turn on the muscle cell. The slower, and you see where I'm going with that. All right. Let's go further. Metabolic pathways. Okay. When we talked about that, the oxidative fibers use aerobic pathways. We just had a discussion on muscle fatigue, and prior to that, we had a discussion in the video before that on energy sources. So oxidative fibers use aerobic pathways. Remember, those are the ones that you can go for hours, 26-mile marathon. The glycolytic, though, you only go a short time, because all you're dealing with would be the ATP already in your muscle cell. We said about 6 seconds. Then the creatine phosphate, we said about 15 seconds. And then the glycolysis, and we said about 45 seconds to 1 minute. So see, all you're getting out of it, let's say, is a minute and a half if you don't have oxygen. But you can go hours if you have this. Duration. Let's go further. All right. So based upon all of this, we kind of have three types of fibers. Based upon this, we have three types of fibers. Let's look at it. Okay, three types of fibers. We have what we call the slow oxidative, and you can study this, the fast oxidative, and the fast glycolytic. Okay? So we have three types of fibers that we have. Okay? Try to make this a little bigger. All right, not too big. All right. The slow oxidative, this is what we're looking at now. The slow oxidative, so I'm going to come here. Remember we talked about fast twitch, slow twitch, so forth like this? So the slow oxidative, the other name for them, authors call it, are slow twitch fibers. Slow twitch. Something like this here, slow twitch. Now, their contraction is slow, but their endurance is good. The ATP is broken down slowly. What does that do? Give you more efficiency. Okay? It's aerobic. See, that's that oxidative. Myoglobin, that's the red stuff in muscle. And these have a lot of myoglobin. Myoglobin stores oxygen in your muscle. It takes it off of hemoglobin, you'll see that in ANP2, and stores it. So you got a nice little storage of oxygen in these. So even though you got oxygen coming from the blood vessels, you also have a little supply up in there. Glycogen is low. You don't have a lot of glycogen because you primarily are getting more out of what you have already. Rate of fatigue slow. Good endurance, ladies and gentlemen. Structural. The color is red. Why? A lot of myoglobin. The fiber diameter is small. You say, what's the advantage? Go back and talk about my surface to volume relationship. If you don't remember, let me say this. Okay. If you don't remember this, let me say this. So small. Okay. I'm going to come over here and put a new slide and let's talk about that. Surface to volume. All right. Now, surface area is a squared term. What does that mean? Length times width. Length times width. So if you say what's the surface area, you do length times width. Okay? So coming back, where to go? That would then equal to, let's theoretically say, x squared. X squared. That would theoretically lead to, let's say, an x squared. Okay? I'll put it here since I don't see it. X squared. Okay. What's volume? Volume equals to a length times width times depth, let's say. So it's a cube term. X cubed. Okay? That means the bigger an enclosure gets, like a room, even though this will get bigger, this will get a lot bigger. Okay? Why? Because this is cubed. So, and think about a cell. Where does it get its oxygen from? The outside. Where does it get its nutrients from? The outside. Where does it get its waste from? So the surface to volume relationship is the reason cells can only get so big. All right. Now, if I come over here real quick, we say, then if a cell is smaller, it has a better surface to volume relationship, which means oxygen has more availability to come in than a big cell. And what we're trying to get? Endurance. A lot of mitochondria, a lot of capillaries. Okay? Running out of time on this video, so we're going to pick right back up on this subject in the next one.